All right, good afternoon. Welcome back to Applications of Calculus 2. Today we're going to talk a little bit more about chain rule and see about what's looking at that. Okay, so I thought I would do a couple more examples that are a little bit more involved in chain rule. I talked about it a little bit in the previous videos. So that way you can see, you can kind of feel how important those are. But the idea of chain rule, okay, is we have an f of g, and we're taking the derivative of this composition of functions. So it's looking at f of g of x, and when I want to take the derivative of f of g. So what's going to happen is we take the derivative of the outside of the original function still sitting in there times the derivative of the inside function, and that's pretty much how this tends to work. So let me go ahead and do a couple of examples for us. So what if we have, I want to take the derivative of, let's see here, we have the square root of 3x squared plus 5. Okay. Now, the first thing I'm going to do with this is I'm going to say, you know what? I would love to make this look like a calculus problem rather than an algebra problem. So I'm going to convert the square root to a 3x squared plus 5 raised to the 1/2 power. So that way I can see what the exponent actually is and work with this. So when I take my derivative, again, we're just using the power rule. The 1/2 comes down in front. Don't touch the inside function yet. Okay, that's still sitting there. And we reduce the exponent by 1. 1/2 minus 1, if you have 50 cents, and then you loan out $1, you are now in debt 50 cents. Okay, and that's how that works. And then we're going to have to take the derivative of the inside. So we take the derivative of 3x squared plus 5. That's going to be 2 times 3, which is going to be 6x to the 1. You don't have to write the 1. And the derivative of the 5 plus 5, that's a constant. So that derivative is going to be 0. And let's go ahead and clean this up a little bit. We have 6 over 2. That's going to give me 3x. And then we have a 3x squared plus 5 raised to the negative 1/2 power. If I had more calculus to do, that's where I would want to put this. If I wanted to say, present this this is my final answer, or I had to solve an equation with this thing in it, I would go ahead and say, okay, this is going to be 3x over, because it's a negative exponent, divided by the square root, because that's the 1/2. The negative sign, put it on the bottom. The 1/2 made it a square root of 3x squared plus 5. And then that would be my final answer. And again, depending on what my next step is going to tell me like, what else do I want to do with this? If for some reason I needed to take a second derivative, I would want to keep it in the fractional exponent form like this, because this is an easier format to take a derivative in than converting it to a square root. If I wanted to solve an equation, um, my pattern recognition for algebra tends to work better with my square root sitting like this. So that tends to be better for me. So I would convert back to what makes it look like an algebra problem in order to be able to solve what the next step was. Okay, so it's entirely dependent on what your next step is what's going to happen. All right, so let's see here. What if I wanted to take the derivative of, I want d by dx, and we have e to the 2x plus 1. Let me show you a little bit of a trick here. We're going to say let u equal 2x plus 1. All right. And then as soon as you make a substitution in calculus, you take the derivative of that substitution. Okay. And that just equals 2. All right. So if I wanted to convert this a little bit, we would say, okay, we're going to take the derivative with respect to u of e to the, well, I want to still take it with respect to x. D by dx. Okay. It's just that u is a function of x. Okay. Of d by dx and e to the u. That's going to be e to the u du technically by dx. So that's what this would really be, is du by dx. So we took the derivative of this u function here with respect to x. So du by dx. And that's our chain rule. So to back this thing out, this answer is going to be, we're going to say this is going to be e to the u du, and we'll just go ahead and back out what we've got here. So that's going to be e to the, what was u? It was 2x plus 1. Du is just going to be 2. So clean this up a little bit and say this is 2 e to the 2x plus 1. Okay. We're going to get into this a little bit more with integrals, but I'm going to urge you when you make a substitution, please declare your substitutions. Don't just assume that everybody is thinking exactly the same way that you are. And well, that was the obvious choice for you. Like, well, for you, that was the obvious choice for you. That may not have been the obvious choice for the next person. So you always do this, let you equal, and that way people can follow your work so that they don't have to worry about like, well, it was the obvious one. Like, I know there's some obvious ones, but it's not always obvious. And when I teach the calculus for the scientists and engineers, I was taught very specifically what to do with certain situations. And like everybody from New Mexico Tech does it that way. When you come to CNM, because everybody has a different teacher for Calculus 1, everybody does it different. So like I look at some of the things that they did, and my only thoughts are like, who hurt you? Like, oh, your Calculus 1 teacher hurt you. That's how that worked. So try to declare your substitutions when you make them so that people can follow along with your work. Okay. My next one will be like, say we have a bacterial colony. So we have a bacteria colony that grows, whose population can be modeled as P of T is equal to, let's see, 100 e to the 0.03 t. And I want to know what the growth rate of this population is at 10 minutes. T is in minutes. T in minutes. Okay, and we want to know what the growth rate is. What is the growth rate at T equals 10 minutes? Okay, I'm going to say, I don't know what the appropriate unit for P is going to be, whether or not that's going to be square inches. I doubt it's going to be cells because I don't think you would go off and count 100 cells, but you guys are biology majors and you would know this more than I would. But if it's going to be, like say square millimeters, something like that, that might be the way to go with this. It would be like it's for increasing it 100 e to the 0.03 t square centimeters or square millimeters per minute. And we want to know what the per is. We want to know what the per minute is. So this is just the population growth at a particular t. I can get, is it going to be cells? Is it going to be square millimeter? Whatever it's going to be. Okay. So we would say, what's the growth rate? We have to take a derivative. So P tick, right, the growth rate of this biology, by this bacteria, is going to be this derivative. So that's going to be 100 e to the 0.03 t, and that because that's the derivative of my e function, right, my exponential function. And now I need that chain rule. And what is the derivative of 0.03 t with respect to t? And that's just going to be 0.03. So 0.03, and we can go ahead and clean this up a little bit. So we have 100 times 300. That's just going to be 3 e to the 0.03 t. That's my growth rate. And then we have to plug in t equals 10 minutes. Okay. So we're going to go ahead and do that. So my P tick, right? My growth rate is going to be 3 e to the 0.03 times 10. Okay, and this is what I'm saying, like you have to be better at math, better at arithmetic, because typing all of this into the calculator, that's going to introduce some human error. So we go ahead and simplify as much as we can before we go into the calculator. That's what works for me. Okay, you can spend more time in the calculator. That's okay. You're allowed to do that. So I just know that this is a really easy problem that is factors of 10. So it's just going to be 3e to the 0.3, 0.3. And then we've already put the 10 in there. So it's just going to be this value. And we will just go ahead to our calculator. You're not allowed to use this fancy of a calculator, but I don't use anything on this calculator that you don't have access to on your calculator. So we have 3 times second function ln, and that gives me a little e button there. And we're just going to type in 0.3, enter. And we've already said the t was 10 minutes. That's how we got this 10 up here, and that's how we changed what the value of the exponent was. So we just plug that in there and we got that. And again, whatever units is going to be. So now it's a per because we're at growth rate. So we have 4.04 here. So I will say 0.05. That last digit was a 9. So 0.05. And then again, this could be in cells. This could be, I think we decided this was millimeters squared per minute because my t was in minutes. And we're taking a derivative with respect to minutes. Okay. So that's how you would go ahead and solve a rate of population growth problem using the chain rule. And that's probably good enough for a video about the chain rule. So again, I urge you to practice, and we will meet back when I think we're starting to talk about integration. So thank you very much for watching the video, and I will see you in the next one.